Alright, so today we're going to be learning about ideal gases. So there's a theory called kinetic molecular theory, which states that all matter consists of tiny particles that are in constant motion. And we make this assumption of gases in terms of kinetic molecular theory, or KMT. And that's that they are particles in a gas are small, hard spheres with an insignificant volume. The particles are far apart, and there's no attractive or repulsive forces that exist between the particles. The motion of the particles in a gas is rapid, constant, and random. Gases spread to fill their space, and particles travel in straight paths until they collide with something. And that all collisions between particles in a gas are perfectly elastic. Kinetic energy is transferred without loss. So kinetic molecular theory has those assumptions of gases, that particles in a gas are small, hard spheres with insignificant volume. The motion of particles in a gas is rapid, constant, and random, and all collisions between particles in a gas are perfectly elastic. Okay, so that is the idea behind kinetic molecular theory, which has to do with one of the theories that we have with gas laws, is the idea behind kinetic molecular theory. Now, ideal gases are said to conform to all principles of kinetic molecular theory at all temperatures and all pressures, meaning that they should have no volume, no attractive forces, and they're going to spread to fill their container. Okay? However, no such ideal gas actually exists. But there's a good thing, because otherwise there would be no point in learning this. Many real gases can behave like ideal gases at specific temperatures and pressures. So ideal gases that conform to all theories of, or all principles of kinetic molecular theory at all temperatures and pressures doesn't exist. But many real gases behave like ideal gases at specific temperatures and pressures. Real gases differ most from ideal gases at low temperatures and high pressures. So those are the situations when real gases differ the most. Okay? So because of this idea of kinetic molecular theory and wanting behavior to respond like that, we actually have an ideal gas law. The ideal gas law allows us to determine the amount of gas present in different conditions, something that we had assumed constant in other gas laws, like Gay-Lussac's and Boyle's law and Charles's law. In order to do this, though, we have to apply a constant. That's the ideal gas constant, and it's given by the symbol of R, and it's either 0.0821 liter atmospheres per mole Kelvin or 8.31 liter kilopascals per mole Kelvin. The key difference being in these two equations the unit of the pressure constant, or the pressure value in the constant. So if your pressure values are in atmospheres, you're going to use the 0.0821 R constant. If your pressures are in kilopascals, you're going to be using 8.31. Okay, so in order to actually be able to use the ideal gas law and the ideal gas equation, we have to apply that constant to an equation. That equation is probably one of my favorite equations, besides MCAT, because it's another one that I have a little phrase for, and it's just funny and stupid, but it helps me to remember it, and that's PERV-NERT, or PV equals nRT, PERV-NERT. And so this equation is our ideal gas equation. It's completely separate from PV, from P1V1 over T1 is equal to P2V2 over T2. Two totally separate equations. PV equals nRT is the ideal gas equation. It's used, you can use it in many situations with real gases to figure out the number of moles. That's the key difference in here, is yes, there's a constant applied, but the PV and the T are the same as our other gas laws, but now we've applied the number of moles and a constant to it so that we can actually solve for the number of moles. So P is still pressure, and again, this can have a lot of different units: kilopascals, atmospheres, torrs, a bunch of others. Volume, we could be in milliliters, liters, centimeters cubed, etc. Now, in order for us to use this, we actually have to keep it in terms of liters, because that's what our R value is in. Moles, N is moles, which is moles. And then R is our gas constant, liter atmospheres per mole Kelvin, or liter kilopascals per mole Kelvin. And then our temperature has to be in Kelvin. So the pressure can be in kilopascals or atmospheres based on our two gas constants, and the volume has to be in liters, but you can convert it from any other volume. And so we're going to use this very much so like our other gas laws, but we're going to be able to use it to solve for the number of moles. I'm not going to expect you to figure out if a question is this an ideal gas or a real gas, or can we use this equation or not. If I'm giving you moles, you can go ahead and use the ideal gas equation. If I'm asking you to solve for moles or grams, you can go ahead and use the ideal gas equation. I wouldn't give you a situation where you couldn't use it. It wouldn't be a trick question like that. So we're going to practice using this tomorrow, so be prepared to come in and use PervNerd. Alright guys, have a good night.